Welcome to GenAI Level Up, the podcast where we decode the future of artificial intelligence one breakthrough at a time.
Whether you're just starting your AI journey or you're a seasoned expert, you've come to the right place. Our mission is to make the complex world of generative AI accessible to everyone, everywhere.
In each episode, we dive deep into the foundational concepts, the latest research, and the transformative applications that are shaping our world. It's time to get smarter, faster. Let's level up together.
Welcome to the deep dive. We are jumping straight into really one of the toughest nuts to crack in AI right now. Continuous learning. You've got these incredibly powerful large language models, but how do you keep them learning, adapting without, spending a fortune and tons of time on constant fine-tuning? It's this fundamental problem of cost, but also rigidity.
Exactly. It's the big hurdle. If we want to move beyond models that just, answer questions and get to systems that can actually do things, tackle complex tasks out in the world. And that brings us to today's source material. It's a really interesting research paper introducing something called Memento.
Memento, like memory.
Precisely. And it's proposing a novel way, they claim, to get this low-cost continual adaptation.
Okay, so the solution isn't tweaking the giant model itself.
That's the core idea. Not through gradient updates or constant fine-tuning, but by using an external memory that grows over time, guided by reinforcement learning principles.
Right. So our mission for this deep dive is really to unpack that. How does Memento use this external memory idea inspired by how we learn, right? Human memory.
Yeah, specifically something called case-based reasoning.
Okay, inspired by human memory to help these LLM agents get better at complex stuff like deep research tasks in real time. It sounds like a clever shift.
It really does. It's focusing on learning from experience rather than just brute force retraining.
Okay, before we get into the Memento solution itself, let's just quickly clarify what we're talking about. We sometimes say LLM, sometimes LLM agent. They're different, right?
Oh, definitely. An LLM agent is much more proactive. It uses the LLM, sure, for its reasoning power, but it acts autonomously. It performs complex, multi-step tasks.
So it interacts, makes decisions?
Exactly. And crucially, it often uses external tools to get things done. It's less like a calculator and more like a research assistant that can go find information and act on it.
Got it. So it's not just answering what's the capital of France, but doing something like research the main economic drivers of France and summarize them?
Precisely.
Yeah.
And that's where the current limitations really bite. The paper points out two main ones. First is what they call rigid workflows.
Meaning the agent can only do exactly what it was pre-programmed to do.
Pretty much. A lot of current agents have these hard-coded reasoning steps. They work great for that one specific thing, but throw them a curveball, new information, a slightly different goal, and they get stuck. They can't really adapt on the fly.
So they're brittle.
Yeah, brittle's a good word. And the second limitation is the computational intensity of adapting them the old way.
Which is?
Updating the LLM itself, using techniques like supervised fine-tuning or reinforcement learning directly on the model's parameters.
Which we already said is super expensive and time-consuming.
Hugely expensive.
Yeah.
And it's just not practical for continuous real-time learning. Plus, you run into that classic problem of catastrophic forgetting.
We're learning the new stuff makes it forget the old stuff.
Exactly. You teach a task B, and suddenly it's terrible at task A again. It's a major headache.
So Memento is basically saying, let's sidestep that whole parameter tuning mess, build agents that learn continuously from their environment, but without that crippling cost.
That's the core challenge they're tackling. And their inspiration, as you mentioned, is human psychology, case-based reasoning, or CBR.
How does that work in humans?
Well, think about it. When you face a new problem, you don't usually start from absolute zero, right? You think back, have I seen something like this before? What worked, what didn't?
Right, you recall similar past experiences.
Exactly. You encode experiences, the situation, what you did, what happened as these sort of mental cases. Then you retrieve relevant past cases to guide your decision now. Memento tries to replicate this.
So instead of retraining the model, it builds this library of past experiences, successes, and failures.
A case bank, they call it. And it learns to leverage that bank to make better decisions next time.
Okay, that makes conceptual sense. Let's dig into the how. If they're not changing the main LLM, what's the architecture? The paper mentions a planner-executor setup.
Yeah, that's the basic structure. It's a two-stage process, which is fairly common in agent design. You have a planner.
Usually a powerful LLM like GPT 4.1 they mentioned.
Right. Powerful one to handle the high-level thinking. Its job is to figure out the overall strategy, break down the task into steps.
Okay. And then the executor.
The executor is typically a smaller, faster, maybe cheaper LLM, like the O4 Mini or O3 models they used. Its job is just to execute the specific subtasks defined by the planner, including calling those external tools we talked about.
Got it. Planner strategizes, executor does the legwork, but where does the memory fit in? That's the Memento magic, right?
Absolutely. This is where they introduce the Memory Augmented Markov Decision Process, or MMDP.
Okay, MDP Markov decision process. That's standard reinforcement learning stuff, isn't it? State, action, reward.
It is. That's the basic framework for how an agent learns through interaction. The agent is in a state, it takes an action, it gets a reward, it moves to a new state. The memory augmented part is Memento's key addition.
Which is the case bank.
Exactly. They add this memory space, the case bank, which is constantly growing. It stores the agent's past experiences, state, action, reward triplets. And having this memory fundamentally changes how the agent decides what action to take next.
So walk me through that loop.
Sure.
An agent using Memento gets a new task. What happens?
Okay, it's basically a four-step cycle that repeats. First, retrieve. The agent looks into its case bank and pulls out one or more past cases that seem relevant to the current situation.
How does it know it's relevant? We'll get to that.
We will. Step 2 is reuse and revise. The planner LLM takes the current task and the retrieved cases as input. It uses that past experience, whether it was a success or failure, to help generate a better, more informed plan for the current task.
Okay, so learns from the past example, then.
Step 3, the executor carries out the plan, takes the action, interacts with tools if needed. Then the agent evaluates the outcome. Did it work? Did it move closer to the goal? What's the reward?
And 5.
Finally, retain. The agent takes this new experience, the state it was in, the action it took, the reward it got, and stores it back into the case bank as a new case.
So the case bank gets richer and more useful over time.
That's the idea. Continuous improvement through experience accumulation.
Okay, back to that retrieval step.
Yeah.
How does it find the right memory? You said there were 2 ways they tried, non-parametric and parametric.
Right. The non-parametric way is pretty straightforward. It just finds the K most similar past cases based on semantic similarity. It calculates how close the embedding or representation of the current state is to the embeddings of past states in the bank.
So it finds the situations that feel most like the current one.
Basically, yes. The K nearest neighbors in terms of meaning.
And the parametric approach. Sounds fancier. Q function.
It is a bit more involved. Instead of just similarity, the parametric approach tries to learn which memories are actually useful for achieving high rewards. It uses a small Q function, kind of like tiny neural network.
Wait, a neural network? I thought the whole point was no costly updates.
Good question. It is a neural network, but it's tiny compared to the base LLM, and it's updated online continuously. The key is that updating this small Q function, which only learns the utility of retrieving certain memories, is computationally trivial compared to fine-tuning the billions of parameters in the main planner or executor LLMs.
Okay, I see. So it's a lightweight update focused purely on making retrieval smarter, selecting cases based on predicted usefulness, their Q value, rather than just similarity. It's a calculated trade-off.
Exactly. It's a differential memory mechanism, as they call it, a manageable overhead for potentially much smarter memory retrieval.
Makes sense. And for these agents to do complex research, they need tools. What kind of tools did Memento use? They mentioned an MCP protocol.
Yeah, the tool suite is pretty comprehensive. For grabbing information, they use things like the Surixing meta search engine and a web crawler called Crawl4AI.
So serious web searching capability.
Definitely. And importantly, they included multimodal tools. Vision language models to understand images, transcription for audio, parsers for digging data out of spreadsheets and PDFs, even code execution in a safe sandbox.
So it can handle real-world messy data, not just text.
That's crucial for the kind of deep research tasks they were targeting. You need to be able to process information in whatever form it comes.
All right, theory sounds good, architecture makes sense, but does it actually work? Let's get to the results. How did Memento perform on those benchmarks?
This is where it gets pretty compelling. The results were strong across the board. On GAIA, which tests long, complex tasks requiring tool use.
That one's known for being really tough, right?
Extremely tough. Memento achieved the top rank on the validation set, with almost 88% success rate, pass at 3, and a very solid 79.4% on the private test set. It significantly beat other well-known agent frameworks like Manus and A-World.
Wow, okay. Almost 80% on GAIA test is impressive. What about actual research skills, the DeepResearcher benchmark?
There, it focused on web research and synthesizing info. Memento got a 66.6% F1 score and over 80% on partial match. The really striking thing, though, was the comparison.
Compared to what?
Compared to a standard baseline using chain-of-thought prompting plus reg retrieval augmented generation, Memento nearly doubled the F1 score of that baseline.
Hold on, RAG itself uses external knowledge, right? Pulling documents, why is Memento's memory so much better?
It's a different kind of retrieval, really. RAG usually pulls in factual snippets or documents to help the LLM answer a question about something. Memento's case bank pulls in past plans and actions, successful or failed ways of doing something similar.
Ah, so it's learning procedural knowledge, how to act, not just declarative knowledge, what is true.
Exactly. It's learning better strategies from experience, which, combined with the tools, made a huge difference on DeepResearcher.
Okay, better planning. Did it help with factual accuracy too? Like reducing hallucinations?
They tested that with simple QA. And yes, Memento hit 95% accuracy, which was a new state-of-the-art for that benchmark. It showed that refining the process with case-based memory helped ground the agent and reduce those instances where web agents just make stuff up.
Good. And the big one, HLE, Humanity's Last Exam. That tests really niche, expert-level stuff.
Right, very long-tail reasoning. Memento got 24.4% partial match, which ranked second overall. And get this, it was less than 1 percentage point behind the reported score for GPT-5.
Whoa. Okay, so this memory approach allows it to compete at the very highest level, even on specialized expert tasks, just by learning from its own generated experiences.
It really demonstrates strong generalization capabilities. It can turn its episodic experiences into reusable skills.
And speaking of generalization, you mentioned the out-of-distribution results were particularly strong.
Yeah, this is crucial. They tested it on datasets like music, Bamboogle, PopQA tasks that were designed differently from what it had seen during its training or experience gathering phase.
So truly novel challenges.
Exactly. And across these O datasets, adding the case-based memory consistently gave significant boosts in performance, anywhere from about 5% to almost 10% absolute improvement.
That really drives home the point that it's not just memorizing solutions to specific problems it's seen before, it's learning a more general problem-solving skill.
Absolutely. It proves the memory mechanism helps the agent adapt and generalize effectively.
Okay, the performance is clearly there. But you mentioned some surprising findings came out of the analysis too, things that challenge common assumptions.
Yeah, the ablation studies where they turned different parts of Memento on and off were really insightful, maybe even counterintuitive in places.
Like the finding about how much memory to use. They tested varying K, the number of retrieved cases. I guess more past examples is always better, right? More context.
That's what you'd think, but nope. They found performance actually peaked when retrieving just a small number of cases. Specifically, K4 was the sweet spot.
Only 4 examples. What happened when they used more, like 32?
Performance flattened out or even slightly decreased.
Decreased? Why would more relevant information hurt?
The paper suggests it's about noise and focus. Remember, those retrieved cases get fed to the planner LLM. If you feed it too many cases, even if they're somewhat relevant, it might dilute the really crucial signals.
The planner gets overwhelmed or confused by too much context.
Kind of. It struggles to extract the key insight if it's buried in a pile of less relevant examples. It leads back to this idea of needing small, high-quality, really potent memories, rather than just a huge volume of vaguely related stuff.
Quality over quantity for actionable memory. That's a neat insight. What else surprised you?
The token burden. We talked about Memento being computationally cheaper because it avoids fine-tuning. But using it for complex tasks still has a significant cost, just a different kind.
In terms of the input needed.
Exactly. They found that moving from simpler level 1 GAI tasks to complex level 3 tasks caused the average input token count to explode. It went from around 26,000 tokens for level 1,
which is already a lot,
to a massive 121,000 input tokens on average for level 3 tasks.
Wow, 121K input tokens. Even if retrieval is cheap, processing that much context for every step must have real implications for latency and cost, right?
Definitely. It highlights that complexity doesn't come free. The paper explains this input bloat mainly comes from needing to integrate all the outputs from the tools, the web search results, the data from parsed files, image captions, plus the history of the reasoning process itself.
So the cognitive load is in understanding the complex situation and the retrieved data.
Precisely. Interestingly, the output token count stayed pretty stable. The heavy lifting is on the input side, making sense of everything.
Okay, one more really counterintuitive finding, the fast think mode. This was about the choice of LLM for the planner.
Yeah, this one really goes against the grain. They compared using the big, powerful GPT 4.1 as the planner versus using a smaller, supposedly more deliberative model like O3.
And the result?
The fast, less complex GPT 4.1 planner actually performed better on average. It got around 71% accuracy, whereas the slower, more thoughtful O3 planner only managed about 63%.
Why would the faster, maybe less deep thinking model be better at planning? Shouldn't more deliberation lead to better strategies?
The paper's analysis suggests it's about the specific roles in the planner-executor architecture. The system works best when the planner gives clear, concise, structured instructions for the executor to follow.
And the faster model did that better.
Apparently, yes. The more deliberative O3 model tended to generate plans that were maybe too verbose, included unnecessary context, or sort of blurred the lines between planning and executing. They called it role confusion.
Ah, like the planner was trying to do too much, maybe getting into the weeds that should be left to the executor.
Yeah.
And that just confused things downstream.
That seems to be the interpretation. The faster model, perhaps because it's just trying to generate the plan structure efficiently, produced cleaner, more directly executable instructions, which worked better with the specialized executor.
So concise and structured wins over verbose and overly detailed, at least in this two-stage setup. Fascinating.
It really is. It suggests that just throwing more thought at the planning stage isn't always the answer. The structure and clarity of the plan matters hugely for execution.
Okay, let's try and wrap this up. What's the big picture takeaway from Memento?
I think the core takeaway is that Memento presents a really viable alternative path for getting LLM agents to learn and adapt continuously. It's efficient, it scales, it's grounded in cognitive science.
And crucially, it avoids that crippling cost of constantly fine-tuning the base models.
Exactly. It shows you can get high performance and continuous skill improvement by building this external episodic memory, the case bank, and learning to use it effectively.
So thinking about the future, what Memento suggests is that progress in capable AI agents might rely just as much on designing smart memory systems as it does on building bigger LLMs.
I think that's a great way to put it. It's not just about scale, it's about architecture, and particularly about how these systems learn from experience in a smart, efficient way, like humans do.
Which brings us to our final thought for you, the listener. Memento demonstrated the power of learning from a curated set of past successes and failures, prioritizing small, high-quality memories.
So the question to mull over is, how could you apply that principle? This idea of systematically learning from specific past wins and losses, focusing on the truly potent lessons rather than just accumulating information. How might that apply in your own work, your personal knowledge management, or even how organizations make decisions to drive continuous improvement without massive overhead?
Something to think about. That's all for this deep dive.
And that brings us to the end of another deep dive into the world of generative AI.
Thank you for tuning in to GenAI Level Up. If you found this episode valuable, please consider subscribing and leaving a review on your favorite podcast platform. It helps us reach more curious minds like yours.
Join us next time as we continue to explore the cutting edge of artificial intelligence. Until then, keep learning, stay curious, and continue to level up.